Good morning, my name is Morgan, and today I'm going to be talking about Newton's first law of motion. Okay. Newton's first law of motion was also called the law of inertia. It was first formulated by Sir Isaac Newton in the 17th century. The law explains how an object behaves when no external force acts upon it. So pretty much inertia is going to mean when an object is resisting change in its motion. So if an object is at rest, it will stay at rest. If it's moving with no external force acting upon it, it will keep on moving. And a force is a push or pull that causes motion or acceleration. Before Isaac Newton, Galileo had already introduced the idea of inertia, but Newton formally defined it in his book Principia of Mathematica. The law is still being used today in physics and also in engineering. Now that we understand what Newton's first law is, let's see how it connects to other scientific fields.
Hello, my name is Trace Anderson. This is a picture of me right here, and I'm going to be talking about Newton's first law of motion. So this is actually the first of 3 of Newton's laws of motion. And this first one is used as a basic foundation for all of his other laws of motion. So basically, an object that is moving is going to keep on moving no matter what, unless some kind of force acts on it, such as friction, gravity, or anything. So if no force acts on it, it's going to keep going forever. A few definitions related to Newton's laws of motion are friction, which is the resistance that one surface or object encounters when moving over another. And then another one is gravity, the force that attracts a body towards the center of the earth or towards any other physical body having mass. So now I have a few examples. A guy running, handstand. So basically something's gonna keep on moving unless some type of force stops it. Gravity, friction.
Hello, my name is Alexis Guest, and today we're going to be talking about Newton's first law of motion, which is an object at rest stays at rest, and an object in motion stays in motion unless acted on by an external force. Some basic facts are that Galileo inspired Newton's theory regarding inertia, and inertia increases with mass. Basic definitions: motion, an object moving from one place to another as time passes. Rest, when an object stays in one place and has no motion. Basic background: Newton's law was groundbreaking and changed how we think of objects in motion and at rest. Before Newton, people had thought that things only moved if something kept pushing them. They didn't realize they continuously moved until something slowed it down or stopped it.
In this slide, we are going to see how Newton's first law connects to other scientific fields. Newton's first law applies to many specific fields such as mechanical engineering, astronomy, and biomechanics. In mechanical engineering, the law is used to design machines and vehicles that reduce resistance and move efficiently. In astronomy, it explains how planets keep orbiting the sun due to inertia, unless acted upon by gravitational forces. In biomechanics, scientists study how athletes maintain balance and motion unless forces like friction or impact act on them. These fields rely on the first law to understand and improve motion, whether it's a car engine, a planet, or the human body. And the person who made all of this possible was one of the greatest scientists in history, Sir Isaac Newton. And in the next slide, we will be talking more about him.
So a related field that I chose was architecture. And you don't think of this immediately because, they're buildings, they're just standing still. But Newton's first law of motion is used pretty heavily in architecture because you don't want a building falling over. You want it to be stable, balanced. You don't want the wind to blow it over, hopefully. But not only buildings, structures, bridges, any type of something built is going to need to stay at rest and not tip over. So architects have to calculate weight, gravity, and use that to create their support forces such as foundations, beams, etc. So we have a few examples here: the Eiffel Tower, Taj Mahal.
Some related fields to Newton's law would be automotive engineering and also robotics. The principle of inertia is essential in robotics. It shaped how robots are built, programmed, and how they operate. In automotive engineering, an example would be seatbelts and airbags. They help exert forces that gently bring passengers to a stop.
And here we are, Sir Isaac Newton. Here's my picture of Sir Isaac Newton. Sir Isaac Newton was born in Worcester Park, hope I pronounced that right, England in 1642. He studied at the Trinity College, Cambridge, where he focused on math, physics, and astronomy. Newton's major research areas were the law of motion, universal gravitation, and optics. He even invented the reflected telescope. His most famous work is the Principia Mathematica. It laid the foundation for physics. Newton's also a member of the Parliament and later as a master of the Royal Mint. He is remembered as one of the most influential scientists of all time. Newton's first law of inertia remains essential to science and engineering today. Newton's discovery changed how we understand motion, and his law continues to influence modern science, technology, and everyday life.
So a relevant scientist to Newton's first law of motion is this guy named Robert Hooke. He was an English guy. He was born in Freshwater, England in July 1635, and he died in London, England, March 1703. So he lived, 68 years? He studied at the University of Oxford. He was somewhat of a rival with Newton, even though apparently they worked together on some topics. So this guy, Robert Hooke, he worked a lot with elasticity and forces, especially because what he's most famously known for is Hooke's law, which has to do with elasticity. And he not only did physics, he also contributed a lot to microscopy and astronomy. So he did a lot using a microscope. So, yeah. All right.
Relative scientists would be Galileo. Again, he initially came up with the idea of inertia, and so some facts about him is he was born in Pisa, Italy. He became blind later in life. This was suspected to him consistently looking at the sun through a telescope. Some educational facts: he originally studied medicine and later changed to mathematics and natural philosophy. His ideas about motion laid the groundwork for Newton's laws. Some of the research topics: he studied motion mechanics, used objects to study time and acceleration. He's famous for improving the telescope, and he also discovered 4 of Jupiter's moons. And that's it.
Original process. Galileo did his experiments in his lab in Padua, Italy, around 1600. He would have used smooth wooden ramps and polished bronze balls to study motion. His setup would have included a long inclined plane, a water clock for timing, and also distance markers. He would have released the ball to roll down one ramp, and then that ball would then climb the other ramp. By adjusting the slopes, he found that the ball reached almost the same height, proving that motion continues unless something like friction stops it. When the second ramp was flat, the ball would keep rolling, showing inertia in action.
Hello, my name is Trace Anderson, and I'm going to be talking about an experiment done by Pierre Gassendi in 1640. So he used a sailing ship. The equipment was a stone and the mast of the moving ship. And the process was he climbed to the top of the mast and dropped to the stone while the ship was in motion and observed where the stone landed.
So, the original process, Newton's first law, the original lab environment, the experiments were not performed in a lab as we know them today. They were performed in more of a workshop type setting. The equipment would have been things like balls and ramps to observe motion and friction. The original experimental procedures would have been something like rolling the ball down the ramp to see how they gained speed downhill and what slowed them moving uphill.
Original difficulties. Galileo faced a lot of challenges because technology was limited back then. Measuring time was especially hard. Clocks weren't yet accurate, so he had invented a water clock. Safety was also an issue. With the heavy metal balls and wooden ramps, the balls could have slipped or the wooden ramps could have fell down. He had to run his experiment many times just to make sure that the results were reliable. Also, Galileo then used math to interpret his results and explain how friction affected motion.
Difficulties of this experiment was that the ship needed to be sailing smoothly and steadily. Possible injuries were falling while climbing or at the top of the mast. To gather information, there was no video back then, so they had to rely on observers nearby to watch.
The original difficulties associated with Newton's first law, early scientists struggled to prove the law because many still believed that motion needed a constant push. Friction also made it hard to show that objects could move on their own once started. Safety issues would have been things like balls rolling off the ramps during experiments could hit someone or break things. Equipment issues. Early experiments faced equipment issues because ramps and balls weren't perfectly smooth. Information processing issues. Scientists had difficulty measuring speed, distance, and time accurately, so this would have thrown their numbers off.
Original motivation. Galileo's main goal was to understand how objects move and what causes them to speed up, slow down, or keep moving. His discovery of inertia was not on accident. It came from careful experiments and logical reasoning. At that time, people thought that motion always needed a force, but Galileo showed that objects resist change in motion on their own. The people who would have benefited most from this discovery were inventors and technicians, since it helped improve mechanical designs and also technology.
The motivation of this experiment was to prove that Galileo's concept of inertia, which is that moving objects keep their motion unless something stops it. He wanted to give a real-world test of the concept, and who was expected to benefit from this was the other scientists of the 1600s.
The original motivation, original goals of scientists like Galileo aimed to study how objects move and how forces affect their speed and distance. Discovery of Newton's first law was intentional. Benefits of this would have been expected to help scientists and engineers understand motion better. It also later helped improve technology and tools in everyday life.
Original benefits. Galileo's work provided the first measurable proof that an object resists change in motion, what we know as inertia. It allowed scientists to start studying motion mathematically, leading to better understanding of speed, acceleration, and force. His findings influenced later discoveries in mechanical devices, clocks, and even space exploration. It also inspired progress in engineering, astronomy, and transportation.
He gave a good physical demonstration of inertia by showing that the stone would move with the moving ship and land straight down at the base of the mast instead of falling backwards and not moving with the ship. Everything on the moving ship will share its motion due to inertia. So instead of just doing thought experiments, this was one of the first real-life experiments on this topic. It advanced physics by disproving one of Aristotle's previous beliefs that continued motion needs a continuous push.
The original benefits, immediate benefits of discovery. Newton's first law helped people understand and predict how objects move or stay at rest. Laid the foundation for physics and practical applications in machines and everyday life. Immediate advancements. Newton's first law allowed scientists to accurately describe and predict how objects move or stay at rest.
Modern process. Today, the same idea is tested using modern lab tools. Experiments would happen in a physics lab and with smooth, adjustable ramps and motion sensors. Instead of the metal balls, we use air tracks or low-friction gliders. Data is collected using computer loggers and also graphing software. When the glider is released, sensors record the motion and graph it digitally, giving us very accurate results.
So a more modern experiment is one called the inertial delay of self-propelled particles, done in 2018. The location was a highly controlled environment to avoid outside vibrations. It was a physics lab in Germany. So they used a vibrating platform with small robots that they called vibrobots. And they studied the inertia of macroscopic self-propelled particles vibrating on this surface.
Modern lab environment would have been motion sensor labs using digital sensors and software. They tracked position, velocity, and acceleration. Modern experimental procedures, a motion sensor records a cart's movement on a low friction track to show at a steady speed when no force acts on it. Let's see here.
Modern differences. Scientists now have advanced tools like computer simulators and sensors to study motion precisely. Safety has improved as well. We understand why seatbelts and airbags protect us based on Newton's first law. High-speed cameras help us to see how motion continues until another force acts upon it. Computers can process that motion data for real-world examples like satellites, rockets, and roller coasters.
So some modern differences were that in this experiment they used a camera mounted above to record the particles. They had computer systems nearby for real-time data collection. Safety measures, the vibrating plate was bolted to a damped optical table to prevent it from moving around on the table. Modern advancements are that we have electric machines to create environments such as vibrations.
Modern differences, modern advancements, robots rely on accurate inertia models to move smoothly and safely interact with objects. Modern protections, an example of this would be helmets. Helmets prevent injuries by controlling the body's motion during sudden stops or impacts. Modern information gathering, computers can examine collected data, generate graphs, and determine velocity and acceleration, obviously much quicker than a human can. Modern information processing, data logging, software records measurements automatically and generates graphs. Again, quicker than a human can do these.
Modern benefits. Research on inertia helps make cars, planes, and sports safer. It also improves stability and control in modern machines. Fields like aerospace engineering use it for rocket and satellite motion. Automotive and medical industries apply it to crash safety and also in prosthetics. Examples we see every day include seatbelts, airbags, and motion sensors. It's all based on the same principles.
So fields that benefit are the field of self-propelled systems such as microbots and drones. This experiment showed that you must account for inertia and delayed responses, not just an instantaneous force into an acceleration. It showed how inertia affects group movement. Robotics is another field that benefits from this. And self-stabilizing micro robots is something that could spawn from this experiment?
Modern benefits of research. Navigation systems use inertial sensors to guide aircraft, ships, and submarines when GPS signals are unavailable. Other fields that benefit from research: biomechanics. They aid in designing protective equipment and studying human movement. Military technology also benefits, so they can use precise motion control to guide missiles, projectiles, vehicles. Examples of some of the technology: navigation and drones.
Future expectations. Scientists hope to use Newton's law to make transportation faster and safer. Future space research will use motion studies to improve zero gravity travel. The goal is smarter crash prevention systems and more efficient rockets that travel further with less fuel. Galileo's early discoveries are still shaping the future of technology and exploration.
Future expectations are dust mitigation and surface mobility systems for lunar environments. They might use this type of research to develop a robot that can go in Martian environments and stuff like that. Some other potential benefits are any type of micro robot or a self-stabilizing.
Lastly, obviously, anything to do with healthcare would be a benefit. So, the future goals for scientists, one of those would be tracking devices to observe and support human movement for health and rehabilitation purposes. Potential benefits to come are learning, training, and gaming experience could become more realistic by precisely simulating motion and forces. Also, to develop vehicles that reduce energy loss.